first episode of the podcast, Young Voices for Climate Action, part of the twinning project SDG Eco Voyage, Europe's Green Quest. Let's welcome our guests.
Hello, I'm Lorenzo. We are here to face our concern with climate change on a global level.
Hello, we are Nicolas,
Diego,
Francesco,
and Matteo.
and with other European partners, we are a part of an international e-twinning project that brings students and science together to get to the bottom of the issues related to global warming.
Hello, I'm Francesca and I'm here with Federica. We are from the province of Modena in the north of Italy, and we are so pleased to be involved in this project with the other partners.
Absolutely, Francesca. Hello everyone, I'm Federica and I'm highly motivated to be here, considering that lately our territory has been hit by extreme flooding events.
Actually, we are here, Federica, to find answers to all our doubts and address our concerns. So let's start this podcast talk with our invited guest. We are joined by Dr. Gianandrea Mannarini, a physicist and a senior scientist at the Euro-Mediterranean Center on Climate Change, or CMCC in Lecce, Italy. He is a climate expert specializing in the numerical applications for operational oceanography, dedicated to advancing public outreach and ocean literacy.
Hello, and thank you for your initiative. I'm very happy to be here to discuss climate change with you.
Thanks for your collaboration, and let's start with Lorenzo, whose questions investigate the reasons for the climate changes in the latest decades.
Yes, absolutely. My question is about the basics of climate change. Is it an anthropogenic process or just a consequence of some natural cycle?
Let me first state that only the astronomical motions of our planet are truly cyclic. The way it rotates, its journey around the sun, the tilt of the axis, and the shape of the orbit. But the Earth is so much more than just a stone traveling through the void. It's a deeply complex living system. Our planet is made of rock, but it is also defined by its fluids, the oceans and the atmosphere, which act as a massive engine, redistributing heat and moisture across the globe. Even the rocks are not static. As we see from plate tectonics and active volcanoes. Then we have the cryosphere, the ice, and the biosphere, the life, both participating in the planet's balance in subtle but vital ways that science is only now fully beginning to grasp. But over the last 2 centuries, a new force has emerged: human activity. We are rapidly transforming the very composition of the atmosphere and the face of the land, affecting how our planet exchanges energy with the outer space.
And so, considering that human activity has transformed the composition of the atmosphere, which human activities contribute most to the increase of global temperatures today, and how can we compare their respective contributions?
The use of fossil fuels for energy production and heating leads to the emission of carbon dioxide, which is a potent greenhouse gas. This molecule is transparent to incoming solar radiation, but traps part of the infrared radiation the planet emits to maintain its energy balance. The change of land use also affects this balance. If we remove a forest, the natural capacity of the planet to sequester carbon and bury it is reduced. On top of this, human activities also produce great quantities of particulate matter. These tiny particles, such as sulfur and soot, can contribute to either cooling or warming of the planet. The work of determining the relative importance of these contributions is based on multiple observations across decades, in situ chemical samplings, optical and infrared monitoring from satellites, as well as simulations from digital twins that integrate all this information with the dynamics of the coupled Earth system. We can safely say that the leading factor in current anthropogenic climate change is greenhouse gas emissions. Not just carbon dioxide, but also methane, nitrous oxide, and other chemicals. They stem from the combustion of coal, oil, and gas, but also from intensive agriculture. Instead, the role of particulates is highly variable in space and time, and it generally leads to a minor cooling in the post-World War II time. Then, with the air quality regulations in the 80s, passed to clean up the smog in our cities and prevent acid rain, particulates have decreased, unmasking the warming from greenhouse gases, which has accelerated since.
Dr. Mannarini, you mentioned World War II, and wars are still a tragic reality across the world today. Beyond the immediate human and geopolitical consequences, there is also a growing concern about their environmental impact. So, let me ask you, what role do military conflicts play in global warming, and to what extent are these emissions actually accounted for?
Unfortunately, emissions from military conflicts are not reported in a transparent way to the emission inventories. However, a few scientific studies have emerged in the last few years to track the climate impact of conflicts currently shaping our time. The Climate and Community Institute, for example, has estimated that the emissions during the first weeks of the war in Iran totaled 5 million ton carbon dioxide equivalent, roughly equivalent to the annual emissions of 700,000 Italian citizens. Destroyed buildings constitute the largest element of the estimated carbon cost, followed by use of fuel for military attacks and destruction of fuel storage sites. A study by the Queen Mary University in London estimates that the additional emissions from just the first 15 months of the Israel-Gaza war totaled to 33 million ton carbon dioxide equivalent. The largest share, 31 million, of this amount are committed emissions for the post-conflict rebuilding of destroyed houses. The actual military operations during the conflict caused 1.3 million CO2 equivalent emissions, while the pre-conflict activities, such as the Israel's Iron Dome or the Hamas tunnels, costed 0.4 million ton. Beyond these figures, it is likely that indirect emissions, such as vessel rerouting to the Cape of Good Hope due to the tensions around the Bab el-Mandeb Strait, caused massive additional emissions. According to a study published in Science of the Total Environment in 2024 by Boone, the net greenhouse gas emitted during just the first 18 months of the war of Russia in Ukraine are estimated at 77 million ton carbon dioxide equivalent. This amount is in addition to the emissions saved as a consequence of the reduction in traditional human activities across Ukraine's main sectors. Finally, a hidden aspect of war's impact on climate arises from the damage or destruction of monitoring stations. By reducing the number or the quality of available meteorological or oceanographic observations, conflicts result in a significant loss of accuracy for both climate assessments and future projections.
So, taking into account both the conflicts and the human activities we've discussed so far, and the fact that global temperatures have already risen by about 1.5 degrees Celsius, what would going beyond this threshold actually mean for ecosystems and for us as human beings?
First, let us keep in mind the scale of the problem. All the contributions from the worlds I've just mentioned are on the order of 100 million tons of carbon dioxide. Global anthropogenic emissions, though, are about 50 billion tons. So even in a world at peace, we would still have a big issue with climate. Regarding the 1.5 Celsius global warming with respect to the pre-industrial period, there's a special report by the IPCC, published just a few years ago, about the implications of crossing this threshold. The literature anticipates impacts on marine ecosystems, ranging from tropical coral bleaching to a poleward shift in marine species, leading to a reduction in catch potential. The ocean surface will warm faster than the deeper ocean, leading to a reduction in dissolvent oxygen, which affects nutrients and the entire food web. With 1.5 Celsius of warming, both marine and atmospheric heat waves are expected to become longer, hotter, and more frequent. What's really striking is that the IPCC report was published 8 years ago and estimated that 1.5 degrees increase would be reached around 2040. However, both 2023 and 2025 were already quite close to the 1.5 degrees Celsius threshold. And year 2024 even reached 1.6 Celsius. The current expectation is that 1.5 Celsius could become the average warming level of the current decade, the one ending in 2029.
As we've seen, technological progress has accelerated rapidly in recent years. So, at this point, we are wondering, are there any existing technologies that could realistically clean the atmosphere? Or should our main focus remain on reducing emissions?
First and foremost, we should reduce greenhouse gas emissions by quickly transitioning away from fossil fuels. This may look challenging or expensive, but any other solution is more costly or less effective. However, we are aware that the temperature threshold is going to be breached very soon, and to avoid dangerous impacts from this overshoot, it will be necessary to draw down some greenhouse gas from the atmosphere. The most efficient and cost-effective way to do it is via plants. So reforestation and afforestation efforts should be prioritized, along with a halt to soil degradation and urban sprawl. It seems to me that other carbon removal technologies are still in their infancy and not yet mature for being rolled out at a scale. There are ideas to collect carbon emissions and store them even before they enter the atmosphere, right at the place where they are emitted. These carbon capture and storage technologies, as well as the carbon removal methods I mentioned earlier, all face the same issue of long-term storage. So far, the most efficient way to do it was found by nature, ironically enough, through the creation of fossil fuels. Indeed, they are the remains of former plants and algae that lived on our planet millions of years ago and went buried in the soil with all their carbon content. By using these fossil fuels, such as coal, oil, and gas, we are effectively freeing carbon from the geological past into today's atmosphere. This is ultimately why we are driving the planetary balance into disequilibrium. Furthermore, it is important to keep in mind that regardless if we clean the atmosphere via reductions in the emissions of greenhouse gases or their removal, it will take years to decades to see some effect on the global mean temperatures, and centuries to millennia to halt the thermal expansion of the ocean.
Actually, if it could take decades or even longer than a human lifetime to see temperatures stabilize and even millennia to stop sea levels from rising, what happens in the meantime? Will human societies be able to adapt to a world where temperatures keep increasing year after year?
In a runaway warming scenario, which I really do not wish for, we should be worried mostly about tipping points in the climate system. A tipping point is a critical threshold that, when exceeded, leads to large, accelerating, and often irreversible changes in the state of the climate system. It is like standing on a canoe or a kayak. If you lean over the side to look at something in the water, the boat tilts. You can lead quite far and the boat stays afloat. But if you tilt too much, the canoe capsizes. If a climate point is passed, adaptation could be very challenging for large parts of the human population and other species as well. We are already experiencing mass extinctions and the loss of biodiversity on our planet. And this is a threat going hand in hand with climate change. As species disappear, the ecosystems that regulate our climate, such as forests and oceans, become less resilient. This means that protecting biodiversity is not just about saving wildlife. It is a fundamental part of our strategy to stabilize the climate.
And which climate tipping points worry you most for the next 30, 50 years? And are we already approaching thresholds that could make global warming self-reinforcing and potentially irreversible?
Unfortunately, there are several good candidates for becoming a climate tipping point. They include the Amazon rainforest dieback, the disruption of the Atlantic Meridional Overturning Circulation, or AMOC, and the Siberian permafrost thawing. Shifting rainfall patterns and human-driven deforestation can trigger a large-scale transition from the Amazon rainforest to dry savanna, releasing billions of tons of stored carbon into the atmosphere. This, in turn, accelerates climate change by trapping additional heat in the atmosphere, further stressing the forest and reducing its resilience. The result is a self-reinforcing feedback loop that could push the Earth system past a critical tipping point with consequences for the global climate. Another one is the AMOC, which is a huge conveyor belt of heat from the tropics to the high latitudes in the Atlantic Ocean. And it makes the climate in Western and Northern Europe much milder than in Canada, for example. We have evidence that past collapses of the AMOC played a major role in shaping climate transitions. Now, both marine observations and numerical simulations suggest that a slowdown of the AMOC is already ongoing and that a critical point could be reached before the end of this century. The thawing of Siberian permafrost is yet another tipping point because it triggers a positive feedback loop. As the frozen ground melts, it releases massive stores of ancient methane and carbon dioxide into the atmosphere. This sudden influx of greenhouse gases accelerates global warming, which in turn causes even more permafrost to thaw, potentially leading to an irreversible shift in the Earth's climate system that persists regardless of human emission cuts.
We are almost at the end of this interesting interview. But now it is important to focus on how to prevent these tipping points.
Exactly. And building on that, Dr. Mannarini, what are the risks of delaying action? What could happen if political decisions on climate change continue to be postponed?
First, let me recall that climate change disproportionately hits the rich and the poor on this planet. This happens not only because accidentally the most severe impacts such as sea level rise, flooding, drought, intense heat are strongest in countries such as Africa or parts of Southeastern Asia that historically contributed the least to greenhouse gas emissions. It is also because in any country, the poor can afford less means to adapt than the rich. The scientists say that for a given climatic hazard, vulnerability is not equal across society. This is why climate change represents an equity question and acts as a multiplier of social injustice as well. Here, let me just note that social inequity potentially generates conflicts. In turn, as discussed earlier, these conflicts lead to higher greenhouse gas emissions. Thus, if climate change and adaptation actions are not put in place in due time, another positive feedback loop can be activated, leading to an acceleration, a further acceleration of global warming. Then, it is now clear that the longer we linger, the higher the impacts and the higher the injustice and the cost. Every tenth of a degree of additional warming brings impacts and losses that are still avoidable today. We have to act while we still have the window of opportunity to do so.
We appreciate your time and interest in this initial exploration of climate science. Establishing a clear understanding of the causes is fundamental to addressing the problem effectively. In the next episode, we will focus on the impacts of climate change in our territories in Europe. Thanks, Dr. Mannarini, and see you in the second episode of our podcast series, Young Voices for Climate Action.
Thank you for your truly stimulating questions. They were right to the point.